To be your beautiful city and here, but well, I didn't know actually Boris Ustinov for a while. It's not that we didn't talk. We didn't know each other.
So the same group, but
well, you never pay attention to students who are 1 year younger, more or less. We used to start collaborating in '96. Let me also thank other collaborators on the same project, Bodo Palena, Troya, and Victor Guray. So I will be talking about the problem which is pretty old, so it's already, I know, maybe 20 years old. Some statements happen to be right, but they were never proved to be exact. So we had several conjectures about what happens in these ordered systems, but for a long time we didn't know how to prove this precisely. And that's why numerics and actually some theoretical work was also pretty confusing during the years. So first, that's why I will spend most of the time just trying to tell you about the theorem of inclusions, which is pretty primitive to prove, I would say, but it has far-reaching conclusions. And I'll just start naming them. They look outrageously generous, but I think they're correct and they are exact. And then I will try to basically project some of the statements from the theorem of inclusions, how this will play for the problem which is kind of current interest for cold atoms. It's superfluid. Well, it's also of interest for granular superconductors, just depending how you cast the model. For superfluid quasi-glass or mode insulated transitions. What is the topology of the phase diagram and what happens there? So first I will just immediately make one kind of application of the theorem of inclusions, which says it's not possible to have a transition between superfluid and mode insulated states. In general, you can make even more stronger conclusion. Non-transition may happen between the fully gapped state and the conducting phase, whatever the nature of the conducting phase. It's also a quite general statement. Well, then I will discuss whether Harris criterion can explain the global features of the phase diagram, and I will answer just, okay, no. Just depending whether Harris criterion satisfies or violated, doesn't tell you anything, more or less. And you still have to do a separate investigation of what happens in the system. You have to be careful with disorder if Harris criterion is violated, but it doesn't give you the full answer. And then I will discuss peculiarities of how can we explain the shape of the phase diagram close to the tip of the mode insulator for dimensions 1 and 2. Well, in 3 dimensions, the vortex phase mechanism doesn't work, so I'll have to use numerical simulations, and I'll show very peculiar phase diagram for 3-dimensional case. If I have time, or there is some interest, I'll also maybe tell a little bit about weakly interacting gas and speckle potential, which is probably the most realistic experimental realization with cold atoms, how you can do bosons in a random potential. Well, this is just briefly mentioning that there is a lot of experimental activity. Actually, well, probably there is 5 more recent papers, especially from the Rice group, on the same subject. So it's actually already kind of in the experiments, but not yet that many work on the lattice. So it's mostly about, strictly speaking, almost non-interacting. That's why it's single particle property. But people already have the system and the engines. So that's the prototype model, because just speaking generally about disordered systems is nice, but well, this is kind of the prototype model you can think about. So I have bosons hopping on the lattice. So this is hopping matrix element. You have on-site interactions, and I have disorder in the chemical potential. It's not necessarily in general case you can disorder interactions, you can disorder the hopping matrix element. But simply under general grounds, disorder first comes as the strongest disorder ingredient in the chemical potential. There is a small parameter, for example, if you put bosons on an optical lattice, there is a small parameter which says this will come first as a strong perturbation, and only later you'll start worrying about disorder in the hopping. So that's the prototype model. I will assume that disorder is distributed on some finite interval between minus delta and delta. And also, just to make things interesting, I will assume the occupation number is 1. Because if it's not integer, I don't even have the mode insulating phase. But just to have an extra phase on the phase diagram, I will keep occupation number 1. Or just any other integer, but it doesn't matter. So I will assume it's 1. So what are the phases for this particular Hamiltonian? If there is no disorder, well, chemical potential, of course, is irrelevant as long as I have occupation number 1. You can always tune the chemical potential to be exactly at unit filling time. So I have superfluid phase. If hopping is very large and interactions are basically small corrections, so you have superfluid for small values of u. And then you have mod insulator if u is sufficiently big. You simply lock one particle to a site. It's a classical picture, of course, you have quantum fluctuations. But at some kind of large u value of u, you have mod insulating phase. So you have a phase transition from superfluid to mod insulator. Well, then you ask what will happen to this phase diagram if you introduce one extra axis, which is disorder. So it's kind of the bound of disorder, how strong it is. Well, and that's roughly what we knew, I would say, before our work. More or less, we knew that, well, somewhere the transition will happen, but first, there was a big controversy what happens close to the tip. The early work was saying that Bose glass will always intervene between superfluid and mod insulator, but it was kind of at the level of conjecture or the most likely scenario. However, when people did numerical simulations, most of the simulations close to the tip saw superfluid mod insulator transition directly, without no trace of any Bose glass. And I confirm yes, if I run simulations close to the tip on a scale of 200 cube system size, that's as large as we can afford, it's a direct transition from superfluid to mod insulator, undeniable. If you see it numerically in a given system size. But still, kind of, the question mark remains, what happens here? Second, well, there was no data what is the actual shape of the phase diagram in this region. Though there was an early work by Kraut, Trivedi, and separately, just saying that, well, if they take parameters somewhere here, they see superfluid signal, which means if you increase disorder on top of mod insulator, you may promote superfluidity. At least in 1D and 2D, I have a rigorous theoretical kind of argument why this is happening, because you can compute the shape of the phase diagram. But this happens also in 3D as well. And probably the last piece of information which we knew for sure was that, well, the phase diagram starts very, very sharply here. It's almost a vertical wall, saying that, well, the moment you have some disorder, of course, if you have no interactions, ideal Bose gas is a localized state, because, well, for any disorder distribution, you can always create a potential which locally creates a bound state for one particle. But if bosons are not interacting, all the particles will end up in exactly the same localized state. So you are done. And this simply is saying that the moment you switch on interactions, the localized phase very quickly goes away. So you immediately stabilize superfluid, even when interactions are extremely weak. So it's very sharp there. Well, this law is for 3D. It changes, so I think in 1D it's 3/4. So this is for 3 dimensions. With regards to mod insulating Bose glass phase, people were arguing, but again it was never a theorem, it was a kind of, again, a pleasurable argument, that the transition happens when disorder is exactly the same as the gap of the mod insulator. What's for sure that if disorder is bigger than the gap, you will close the gap, because you can dope the system. But whether the transition can happen at a lower value was never proven. So maybe, well, the transition happens not by closing the gap by simply making chemical potential bigger than the gap. That's essentially the statement. You can shift chemical potential locally by an amount bigger than the gap closes. Or you can destroy the gap by some other mechanism. So if this line exists, it has to be below the blue line. Whether it's exactly the blue line, people didn't know. But the conjecture was it is a blue line. So now I will just try to basically fix the shape of the phase diagram, so it will be clearly answered whether you have Bose glass always intervening between superfluid and mod insulator. We'll definitely prove what kind of transition you have here, and maybe just some general statements, and I'll show you numerics how the global phase diagram looks like. So let me start. So the most important piece is just the theorem of inclusions. So the mathematical background which you need to understand the theorem is this lemma. That's all. So if you believe me that this is true, then the theorem will be proved. And this is essentially stating the following. If you have a random potential, you're free to play random numbers on a given side the way you want. And essentially, just no matter what is the model of disorder, no matter what is typical, according to the model of disorder. I'll just say a little bit. Well, because when you decide about the model of disorder, you have to tell me from what distribution you draw a random number to decide about the potential on a given site. You can say, okay, this can be randomly distributed, Gaussian distributed, Lorentzian distributed, can be finite support between minus delta and delta, or some other distribution. But you have to say what is the distribution function. But regardless of the distribution function, the probability of creating anything I like on a given site within the bound is a finite number. Which means that if I take many sites, I can design a disorder configuration in a given region side by side. Anything I like, and the probability will be finite for any model of disorder. So the typical model of disorder can be, say, disorder is randomly distributed on the unit interval. But I can always create a big region and claim that I want disorder to be, say, smaller than 10 minus 6 on every side. It's still a finite probability. So that's the important statement, that if you play random numbers, in any given, no matter how big but finite region you take, you can produce disorder realization, which is anything you like. It's not, it can be completely atypical, but it's anything you can design. And the probability is still finite. Okay, now let's see how all of this works. So let me first introduce the definition. I will consider generic disorder. Well, generic disorder means the following. You can generate a random number within the bound. The bound is important because if you don't have bound, some of the faces are simply do not exist. So bound is an important parameter. So I just do bound that random numbers are between minus delta and delta. But you can draw this random number from any probability density you like. You just design this function, the shape is absolutely arbitrary. So you have infinite dimensional parameter space to design this black function. I do want this function to be non-zero within the bound. How small, I don't care. 10 minus 20, fine. As long as it's non-zero. So I do assume that, well, the support for this function is non-zero between minus delta and delta.
Question.
Yep.
The spectral potential does not have bounds, is that correct?
Yeah. Well, but if the disorder is not bounded, some of the phases are removed, and then some of the statements are not even there. I don't even have to worry. For example, if the chemical potential is unlimited, which means I can create plus infinity, there is no Mott insulator by definition. You will always breach the gap. So Mott insulator is not on the map if I have unlimited potential. I can, when we say speckles, you assume infinite number of speckles. The moment you say I have a speckle potential, which is not exactly random, but you say you have a limited number of speckles, it will be limited in the amplitude as well. Yeah, okay, so now I take this kind of generic disorder, which means bound is the only parameter, the rest is just whatever you like. And I consider an arbitrary transition, but transition is such that transition point depends on the model of this, depends on the disorder properties. So let me start slowly. That's the statement of the theorem, and I will start proving it. So if I take generic disorder and take an arbitrary transition where the transition point depends on how I play this disorder, there will be always regions of competing phase on the wrong side of the transition, which means in phase B, close to the transition point, I can always find arbitrarily large regions where the actual phase is A. So I have inclusions of A inside B. And the theorem works both ways. In A, you will always find inclusions of B. So that's the statement of theorem of inclusion. On either side of the transitions, you have arbitrarily large inclusions of the wrong phase. So let's start the proof. I'll just imagine that my model of disorder is uniform distribution of random numbers between minus delta and delta. So that's kind of the standard model people use for lattice models. You just play random chemical potential between the bounds. So I have a transition from phase A to phase B. I don't name the phases because the theorem is general. Bosons, fermions, spins, I don't care. And there is a transition point from A to B as I increase the bound from disorder. Now it's very easy to prove that I have inclusions of A inside B. That's of course trivial. You take a point in the parameter space. Well, this is phase B for this bound of disorder. But as I mentioned already, inside B, I can always separate as large a region as I want, play random numbers, and simply demand that, well, on every side inside this region, random numbers are mimicking disorder, which is uniformly distributed, but with much smaller bound. the probability is finite. I simply say on first side, the disorder is on a bound which is, say, twice as small. On the second side, same. It's a typical disorder realization of phase A. And because bound is only one thing which is limiting me, I can say, okay, well, actually I'm sitting here. But inside a big region, I'm mimicking disorder distribution happening here, and it's allowed because this one has a smaller bound. So there is nothing limiting me to produce such a region. So which means inside B, I always have sufficiently big regions. Well, the probability can be exponentially small. So right now I am just playing the academic game, not what will happen in the experiment on a given small size or on a computer. I'm saying what will happen in a thermodynamic limit. Because in the thermodynamic limit, I have infinite resources, so I can find, with finite probability, I'll find sufficiently big regions of A inside B. So that's trivial to prove. Well, now I would like to prove the same statement, that inside A I can find B. But I cannot play the bound anymore, because this point has a smaller bound than the blue point. I cannot find a big region where disorder is stronger than the bound, because bound is a strict restriction. The probability is 0 to generate anything else. So how do I play this game? And this was exactly kind of the point which was bothering people. How you prove in the opposite direction. And now you have to introduce an additional axis on this plot, which is models of disorder. It's an infinite dimensional axis. Remember, we are interested in properties of this model. But just imagine that in general, you would like to plot where is the position of the blue line if you change disorder properties. Because, for example, here I have one dispersion. This is much smaller dispersion. This is bigger dispersion. It's simply a different distribution function for the same bound. And if your transition point, where the transition happens, depends on the model of disorder, so you have some line, then I can make the statement that, well, inside A, I will always find regions of B. Well, this looks quite reasonable. In a sense, just, well, okay, this disorder, just imagine this delta function is as sharp as you want, and, I don't know, the integrated weight of the central peak is, say, 99.99999%. Almost everything. But you say, well, it's almost no disorder. Very infrequently you generate something meaningful with sufficiently big fluctuation. Most of the time you generate 0, so it's almost an ordered system. So then, well, your disorder bound probably has to be much bigger before you destroy A. So the transition point shifts to bigger delta. Well, if I take this disorder, it's probably stronger than this one, because, well, you constantly generate pluses and minuses with large amplitude, while here, I know, from time to time you generate small numbers. So probably here the transition point moves to a smaller delta. So if you assume there is some line, it's a multidimensional parameter space. You can also play multi-point correlation function or correlation radius. This model, say, is uncorrelated between the sides. That's the typical. But you can also demand that, well, there is some other model, then disorder is correlated, which means if you generate some number on one side, you just keep generating similar numbers on neighboring sides. So if you have this line, then you immediately say, okay, I'll do the following. From point A, I'll fluctuate down to here. Which means inside A, I will design a big region, and in this region I'll play disorder with a smaller bound, which is always allowed, but I'll play a completely different distribution function as typical for this region. It's completely atypical for the whole system. But the typical disorder realization in this particular region will be here. So which means my typical model of disorder is like this, but in this region, I generate this model of disorder. Again, well, the product of finite numbers is finite, so for any region which you design sufficiently big, the typical disorder realization will be that of B. So it will be the region where the actual phase is B, without violating the bound.
Can I ask a question?
Yeah.
I mean, it all sounds very convincing, at least to me. But you say theorem. Is this, I mean, is this really...
Now it becomes a theorem, because I'm saying if you have a transition line which depends on model of disorder, you always have inclusions of A in B, and you always have inclusions of B in A.
So somehow you're...
Yeah, but you assume that you draw that line for us, and then you make...
No, I'm saying if there is a line.
Yeah.
That's the theorem. The theorem says if you have a line, that's what I said. Transition point delta C depending on disorder properties. It's the preposition. So if I say the preposition is such that there is a line,
You're assuming
Then.
also that there's only two faces there. I mean,
I
what
have a
if-
phase transition from A to B.
Yeah, but what if the form of the disordered distribution creates additional faces?
Well, it's still some phase.
Yeah, but it could be a different face. A phase C.
If I have phase A, whatever your phase you have, you increase disorder and you enter another phase. It's phase B. Yeah, the properties of A, I don't question disorder or properties of A. They are whatever they are. And you have a phase transition to B. For example, this is superfluid. Undeniable, I measure superfluid density. I'm saying I have a transition to another phase through this point, where superfluid density goes to zero. This is my phase B.
I meant more, I mean, you draw the line very suggestively and you argued for it. And
It doesn't matter how this line goes. I don't care if it's this slope, I'll fluctuate up.
No, but if it goes like that.
It's a zero measure. Because remember, this is infinite dimensional parameter space. So you say you design a model of disorder, which happens to be a maximum or extremum in the infinite dimensional parameter space. So as a measure of zero, just take any other model, just, I don't know, modify anything you want, and you are. Yeah, I'll just mention a little bit more. Just, well, that's not there. That's why you have 8. That's why I say if delta C depends on disorder property. So this was important.
Do you have to worry about how the correlation function
No.
for the bosons behaves?
No. I only need the existence of a line, non-zero gradient. But it's an infinite dimensional parameter space. So I would say just, well, if you want to design such a model, I would just give you 0 chances for producing one. Because remember, I'm playing not only the distribution function, you can play multi-point correlation functions. You can play correlation properties, how many sites are correlated. Everything is part of this axis. So generating a model when it's absolute maximum in the infinite dimensional parameter space, no. So I exclude this 0. So that's the proof of the theorem, including the statement that transition point depends on disorder properties. You always find inclusions of the opposite phase on both sides. I can immediately tell you on one of the implications. If A is gapless, B has to be gapless. Because inside B, just suppose I state the opposite. Suppose A is gapless, B is gapful. When I say gapful means, by all possible means, any excitation from the ground state, you have a gap. It's not possible, because inside B you have inclusions of A, and they can be as large as you want. And because they are as large as you want, and A is gapless, B is gapless as well. I'm not telling you what the density of states. It can vanish, I don't know, very sharply, but it's not zero. So which means B is gapless. And the other way around, because well, the theory works both ways. So which means, if you have a transition line, it cannot happen, possibly, between gapful and gapless phases. It can be only gapless or gapful. You may not have the transition line between gapless and gapful. The line which has a non-zero gradient. It's forbidden. So which means this type of kind of behavior cannot happen. So if you have fully gapped state of any nature, you apply any disorder you like, and you try to destroy the gap. You cannot destroy the gap according to this scenario. It's not possible. Non-gap in nature can be closed by disorder if you have a transition line which depends on model of disorder. It's not allowed.
Does the argument change if you have a finite size in the system?
Oh yeah, we'll come to this. Yes, of course. Well, in finite size systems, there are no phase transitions. So I'll start talking about crossovers, and I'll characterize the crossover. So that's the model of inclusions. Now, what is the only possible? Yeah, okay, I forgot to say. This is just well, one extra piece to mention. I still have the freedom, even if I generate this region of phase B, I still have the freedom to adjust the average value, say, of chemical potential in this region. If I'm talking about disorder in the chemical potential, I generate this region, but I still have the freedom of moving the global chemical potential in this region within the bound, because I still have finite distance to the blue. This will be important for me just to say that quasi-glass is definitely compressible. Now let me just mention the second part of the theorem. That's why I have D, which said, okay, what was missing in the previous graph is that maybe, for whatever reasons, but I don't have to exclude this, the phase boundary between A and B is absolutely vertical. And then I do lose the possibility of constructing inclusions of B in A. Because, well, no matter how I try to go in any direction for the model of disorder, I cannot generate phase B. Doesn't help. That's the other kind of possibility which may happen. And I will argue, okay, well, remember on the previous graph I was saying, if I have a line, you may not have a transition between gapless and gapful phases. But then you say, okay, obviously we know that if I start from the gapful ground state and introduce disorder, say unbounded, and increase bounds, sooner or later it will be unbounded, I have to exit out of the gapful phase. I can destroy the gap. But I was saying you cannot destroy the gap according to the previous scenario. So what's the alternative? The alternative is just, well, I fail the assumptions of the previous statement. And the assumption of the previous statement, the only one kind of which was explicit, is just having a line. So I don't have a line, so it becomes a vertical. So the only way I can have a transition between gapful and gapless is to have a vertical line. But you immediately realize this is a pretty peculiar situation. It's definitely not a scale invariant transition. Because locally, this disorder, or this disorder with delta function containing 99.999, locally they are completely different systems. Because this one locally is losing, say, superfluid properties, but this one is almost ideal. And suddenly you say that, well, it doesn't matter what kind of distribution function you have, it still happens at delta C. It doesn't matter whether you have multi-point correlations. It doesn't matter whether you have long correlation properties or short-range correlation properties. All of this is irrelevant. But all of this is relevant for microscopic physics of the phase, which means the transition doesn't happen as the microscopic scenario. The transition has to happen according to the scenario which has nothing to do with typical local properties. And this is what known, kind of in literature, of course, people already know how to describe it. It's called Griffith's type transition. When the transition is driven by statistically rare fluctuations, when you create something atypical. And that's the only way how phase A and B are different. So it's a transition when B and A locally are identical. They have to be locally identical because nothing depends on local properties. And they are different only by finding exponentially rare, close to the transition point, exponentially rare regions which distinguish A from B. Those regions don't happen in A, and those regions do happen in B. And that's the only difference between the two. So it's definitely not scale invariant because locally they are identical, and you can easily kind of tell how close you are to the transition point by looking at the distance between those rare regions. First, they are clearly identifiable, and you can measure the distance between them, and this will tell you how close you are to the transition point. So it's not scale invariant transition by scenario of rare statistical fluctuations. For the Bose-Hubbard model, we know, for example, what will kill the gap in the Mott insulator. This will be a region where disorder is side by side, mimicking a regular field, local change in the chemical potential which closes the gap. So I don't care what is the distribution function, because the region which kills the gap in the Mott insulator is when the chemical potential is at the upper bound in the entire region. There is yet another region where it's at the lower bound, minus delta, and then you can transfer particles from one region to another one. So you create particle in one region and hole in another. So those are the rare regions which distinguish the two phases. But microscopically they are identical to each other. So that's the only other statement for the theorem of inclusions. It's either line, and then you have inclusions on both sides, or it's a vertical line, but then the transition kind of type has to be Griffiths. It has to be a transition which is driven by rare statistical fluctuations.
So that rare process should have a finite congruent elements, yes?
I am talking about ground state at the moment. So which means that, for example, if this is fully gapped phase, for this one, say, fully gapped phase, for small disorder you have a gap. It means that phase B is exactly the same as A, you have gap, except for small regions where this gap is broken, which means B is an insulator. So it's the second statement that, well, if I start from fully gapped state and I go to B, B is an insulator. I cannot enter a metal from the fully gapped state. because the transition is of a Griffith type, and it's now given by exponentially diluted regions. So I enter an insulator. I may not have a superfluid because, well, there is no phase coherence if the distance between the lakes is exponentially large. So it's kind of straightforward statement. From the fully gapped state, I cannot enter superfluid. I can only enter an insulator, which is gapless, but it's an insulator, because the transition line is there. So I think it's also a rigorous thing. And this is it. Well, in particular, for example, for the mod insulator, Bose-Glass transition, you say yes, because we now know for sure, because well, we can close the gap in mod insulator only by Griffith's scenario, mimicking a regular field. The transition has to happen when disorder equals the gap. So it's a rigorous statement, it's not an assumption. Well, this is just basically illustrating what I mean by the Griffith's transition. So you start somewhere, phase A, you approach the transition point, it slightly changes color, but that's it. You go to phase B, you look locally, and you see no difference whatsoever from A, so I have to go on a bigger scale, and then I find rare regions, and those rare regions is the only thing which is different between A and B. Of course, if I keep going further, the number of regions gets bigger, maybe you establish phase coherence between them, so the phase microscopically gets different. So that's what I mean by the transition of the Griffith. Okay, and this is just repeating the same, but well, here I just simply wanted to mention, and I already mentioned that, well, you have a freedom in this picture to move the chemical potential a little bit. So, for example, if this is superfluid and this is Bose-Glass, you immediately see a superfluid is a compressible state, which means adding particles to superfluid has no gap. And actually, it's finite density of states in the superfluid. But if I take a superfluid and create a Bose-Glass, so in this region, oh sorry, I wanted to say the opposite. Doesn't matter. It's the same here. So if I take Bose-Glass, I have regions of superfluid, but I have the flexibility of moving the liquid region with global chemical potential. But it means that whatever energy levels I have in the liquid lake, they can be homogeneously shifted back and forth. So at the chemical potential, when every level just can be shifted by finite amount, you create a finite density of states. So which means that the phase which you create from superfluid has to be compressible. Unless, of course, you don't have the flexibility of changing the chemical potential. This is also possible, for example, if you take a specific model which has particle-hole symmetry, and disorder is not in the chemical potential. So you can design a model when this chemical potential is not a disordered quantity, it's ordered quantity, and you make disorder in the Josephson coupling. You make disorder in the Hoping matrix element, or you make disorder in the coupling between the bosons. I'm not saying it's easy to do, but well, just imagine you have such a model. In this case, I lose the flexibility of changing the global chemical potential of the system. It's absolutely fixed. Then I cannot say that the phase which I create from superfluid has to be compressible. I lose the statement. So it's possible to create incompressible state out of superfluid, but it still has to be gapless. So this is called mod insulator, mod glass. So you have two glasses. But if you have disorder in the chemical potential, it has to be compressible. Okay, well, this is more or less just mentioning what are the consequences of the theorem of inclusion. So let me just repeat it. So if A is gapless, B has to be gapless. If A is gapful, B has to be gapful. That's for the generic line. That's why I just say, okay, it's a generic line which has some slope. If I want the transition between gapful and gapless, it has to be of the Griffith type, and then immediately the consequence is that, well, all faces next to the fully gapped state have to be insulated. So if I close the gap by all possible means, I can close the gap only by the Griffith scenario, and what I create on the other side is an insulator. Well, which means that superfluid to mod insulated transition is forbidden in any dimension, because this theorem doesn't say anything about dimension 1, 2, 3, or 5. So it's forbidden in all dimensions. Well, which means that between the two phases, there has to be some intermediate phase, I'll call it Bose-Glass, which is an insulator. It's gapless because you close the gap in the mod insulator. So it's a gapless insulator. And in general, just if disorder is in the chemical potential, it's compressible. So that's what we more or less attach to the name of Bose-Glass. It's compressible insulator. Well, also for the generic lines, well, that's what I already mentioned, and I also actually mentioned this one. So if I have a gapless phase, but I have particle fault symmetry, maybe my insulator is not Bose glass, but immortalized, which means it's gapless but incompressible. Okay, now I just go back to the previous kind of diagram, and I say, okay, more or less the theorem fixes the topology. The theorem says, okay, Bose glass will always intervene between superfluid and multi-insulator. But there you have seen already that this scenario of, say, multi-insulator Bose glass transition is based on rare statistical fluctuations. And if disorder is weak, those rare statistical fluctuations will simply not fit the system size, they will not fit the simulation size. So if you ask what will happen in a finite system here, you'll see direct transition. You'll see no intervening Bose glass phase between the two. It will be completely impossible to detect in a small system size or in numerical simulation. Because it's based on rare statistical fluctuation, which is exponential in the volume of the droplet, and it's just good luck. You can always check on your computer that you create such a droplet by hand, it will break the gap. So it's always at your disposal, just to say, okay, well, I cannot generate it by simply playing random numbers for 1 year, but if I design it, it will definitely break the gap. So that's now what we have. So we know this law. We still have to figure out the law for the green line, how the green line starts, but the topology is more or less fixed. So let me now mention a little bit about the Harris criterion, because it's used frequently to discuss whether disorder is relevant or not. You have seen from the theorem that superfluid multi-insulator transition is not possible, and there is always another phase in between the two, which says immediately that for any disorder, strong or weak, the original superfluid multi-insulator transition is destroyed. It just splits into two, so disorder is always relevant. You create a new phase. But if I apply the Harris criterion, well, the Harris criterion is basically saying the following. You take sufficiently big volume, and in this volume you calculate mean square fluctuation of some parameter in the Hamiltonian, which is disorder. Well, it's simply by central limit theorem, it says that on average, in this region, your Hamiltonian parameter changes as 1 over square root of the volume which you consider. I'm sorry, this has to be excited power plasma. Oh, that's without the square root, it's plasma. So it's inverse square root volume, that's central limit theorem. Well, but then you say, well, if disorder is to be irrelevant, I have to claim that mean square fluctuations of the Hamiltonian parameter in the correlation length volume have to be much smaller than the distance to the critical point in the ideal system. Which means disorder introduces fluctuations which can change your notion of how far away you are from the critical point. Well, but nothing special happens if this is much smaller than the distance to the critical point, which is itself defined by the correlation length, from the correlation length experiment. Well, you immediately have a condition because you have an expression for this one from the central limit theorem, and you just say, okay, when this is satisfied. This is satisfied when the correlation length is bigger than 2 over d. Well, there is only one difference I have to pay attention to. The d is the dimension of space, but the correlation length for the ideal transition without disorder, because I'm talking about quantum phase transition, and the quantum phase transition I'm discussing now has z equal 1. So it's superfluid multi-insulated transition, which says the time direction is the same as space direction. So in this case, it's 4 dimensions for the correlation length and 3 dimensions for a real space. So you start substituting numbers. Well, you see that nu4 is approximately mean field up to log corrections. So it's less than 2/3. Nu3 for 2 dimensions is given by U1 universality class. It's less than 1 in 2 dimensions. So Harris criterion is definitely violated in d equal 3 and d equal 2. So it agrees with the theorem of inclusions. Well, but if I look at d equal 1, the transition is positive Taurus. So formally it corresponds to nu going to infinity, because correlation length diverges exponentially. So it's formally nu is as big as you want. So it's definitely much bigger than 2. So Harris criterion is satisfied, but still disorder is relevant, and the phase diagram is different. Well, also if I go to, I don't know, higher disorder, non-physical dimensions like 4, 5, 6, Harris criterion will be satisfied, but the theorem of inclusion says, sorry, still the new phase appears. So though Harris criterion is satisfied in some dimensions, it doesn't tell you that disorder is irrelevant. You still have to check. Okay, let me now switch to mechanisms. What happens, for example, in 1D? How you explain the phase diagram in 1D and calculate the shape of the line. So I will start from the Euclidean superfluid hydrodynamic action. Well, it's well known, just well, it's nothing new we say here. So it has two terms. One is conventional kind of gradient of the phase field squared with some stiffness. Well, in 1D it's Lagrange liquid, so very frequently people call this Lagrange liquid parameter. But it plays the same role as in the two-dimensional XY model is played by the superfluid density. So if not for the first term, you are looking at the two-dimensional XY model. Phi is the phase field. Well, Y coordinate in this case is just simply the scale of phi. So if I close the first term, you say, okay, this is conventional XY model which has a Kosterlitz-Tauris transition when the value of K equals some critical value. So it's kind of standard physics. But if you look at the first term actually has the first coefficient is the average density at space point X. So it's not fluctuating quantity, it's the average density. Well, this is the full time derivative because it's just rescaled by this velocity of sound. This is full time derivative. So the question is, why do we keep full time derivative in the action? Because I can take the integral over dy. Well, the point is that phi is a variable which is defined modulus 2 pi. Though this is action, we understand, okay, well, then the phase goes around the system and you go from 0 to 2 pi or to 4 pi to 6 pi, it's still around. It's not that I have to satisfy periodic boundary conditions and come with the phase after I go around the time direction. I have to come to exactly the same value, not at all. It's the phase field, so I have to go by multiples of 2 pi. And then you see that, well, integrating over phi variable over time can bring me multiples of 2 pi. And you immediately see what kind of configurations in the statistics of the phase field will make this term relevant. Well, suppose I have a vortex type excitation. It's very easy for me to picture everything because without this term, it's conventional XY model. And this is just the gradient term for the XY model. So I have vortex type excitation here. Obviously, if I take an integral from here up to here, well, you can imagine taking it as close to the center as you want, turn around and go back. It's a closed quantum. Well, but because those pieces are negligibly small, this is integrating phase field over time. And this is integrating over phase field over time. And makes a closed quantum, but you know it's 2 pi. Which means that integrating over this direction minus integrating over this direction, over this line, gives you 2 pi. Which means in this vortex type configuration of the phase field, this term, the full derivative, changes from 0 to 2 pi as I cross the position of the vortex core. Of course, well, hydrodynamic action is already coarse-grained. So just, well, I simply say, okay, you go from this point to this point, and this one picks a contribution which is 2 pi times the charge of the vortex. So if I have vortex-anti-vortex pair, I have 0, 2 pi in between, and then I have 0 again. So a vortex pair will pick up a contribution which is 2 pi, or I'll say charge 1. 2 pi, an integral over particle density between the 2 points, x1 and x2. So I just explained how the first term will play the game if you have vortex pair excitations. Remember, without the first term, it's conventional Kosterlitz-Tauris, which drives the transition from superfluid to multi-fluid. Now, if there is no disorder, then nx is an integer, so instead of actually taking the integral, you take a sum because I have a lattice model. So this is the reason for the continuum, but well, if you have a lattice model, you simply sum densities on different sides. Well, but if nx is an integer, it doesn't matter how many sides you sum, your phase factor is a multiple of 2 pi, you just don't care. So if nx is an integer, the modulus of gamma 2 pi is 0, neglect this term entirely, and you just say superfluid multi-insulated transition is conventional Kosterlitz-Tauris type. Because you don't care about this term, it's always a multiple of 2 pi. All vortices are in phase with each other. Some people will actually say it's coherent backscattering. Because why do you have those vortices kind of in a lattice system? The particle is scattered back by the lattice potential, but all backscattering events happen in phase. So it's constructive backscattering, if you like, and all vortices play a role. You have a transition to the multi-insulated. Now, if you are in a disordered system, the average density on a given site is not an integer anymore, it's fluctuating. And fluctuations of density build up, so I simply apply a central limit theorem again. Here it's written, I would like to know how many particles I have on the distance of the vortex pair. And you count how many particles. Well, how many extra particles, because, well, any integer has to be subtracted. Well, you see, I will write it down as compressibility on scale r. R is the distance between those 2 points, times the fluctuation of the average chemical potential on the same region. That's the relation between particle number and the chemical potential. So I see that, okay, well, roughly I can estimate how the phase of the vortex pair will keep increasing in the presence of disorder. Because I have 2 pi delta times square root in the distance, so it's central limit theorem. So that's how this field is getting up. It's delta times r to the power 1/2. Inverse u, it's the compressibility of the system. So it's a rough estimate how the phase of the vortex pair will increase if I have disorder. But then you immediately have a scenario. Why disorder is relevant? First, this term, if disorder is very, very weak, you don't care about the phase of the vortex pair. So you start the transition from superfluid to multi-insulator using conventional scenario. So it's post-Lestowitz and normalization group. Proliferation of vortex pairs. Vortex pairs are getting bigger, bigger, and bigger. But as they're getting bigger, some vortex pairs will actually reach this point when the phase of the vortex pair reaches 1. For bigger vortex pairs, they will come with phases which are randomized between 0 and 2 pi, and their total contribution will be killed. The only contribution can be given now by vortex pairs which are vertical in time direction. So which means plus and minus vortex, they have to be on top of each other in time, but you cannot separate them by large distance in real space, because those vortex pairs will be killed by phase factors. So your normalization group flow changes from having isotropic vortex pairs to vortex pairs which are on top of each other in imaginary time. And this immediately results in the following RG flow. I'll just skip details, but they are trivial for the RG scale. So you just say, okay, in the absence of disorder, you have a line, no disorder, you are sitting exactly at the critical value, and your K value, which is analog of superfluid density, is simply just diminishing, and this is the critical value. 2 is the same as Nelson-Kosterlitz criterion for the Kosterlitz-Towers transition. So that's where the transition happens. Well, now if I have some small disorder and I'm actually sitting on the insulator, if I don't have any disorder, or disorder is weak, if disorder is weak and I'm already sitting in the Mott insulator, well, you simply follow the same flow, and then starting from the correlation length, your K value just drops and goes to very small values. You are in the insulating phase. You're done. And disorder is weak in the sense just, well, the phases of vortex pairs are still small on that scale. So on the correlation length, disorder doesn't play any role, and your RG flow takes you to the insulator. Well, but if you increase disorder beyond this value, well, you immediately see that your flow goes as usual. You go to the insulator, you start just going down. But at this point, at this radius, phases of vortex pairs become important, and your flow can change to a value. Well, this is actually the critical value for the superfluid Bose-Glass transition. Or actually, well, if the flow will change even here, you can saturate to a value which is sufficiently large, corresponds to superfluid. So that's the mechanism, actually, well, how disorder can stop the RG flow to the Mott insulator. And you immediately have the estimate of what are the boundaries. All I have to say that, okay, this was radius to power 1/2, but the Kosterlitz-Towers transition has real space and imaginary time, or energy space, they are equal to each other. So simply replace the correlation length with the gap of the Mott insulator, because that's the transition which you have in the clean system, and you immediately check when the vortex pair phase is a Fourier unity. This gives you the criterion when the transition happens, when we change the RG flow to the Mott insulator. Well, this is the typical scaling, which says disorder has to be roughly square root in the gap of the Mott insulator. So this establishes the law for the transition line. Well, this is just the sketch of this. So the transition line for the ideal superfluid Mott insulator is just the equation for the gap. Remember the theorem, well, it has to happen by Griffith's scenario when disorder equals the gap. Well, the gap behaves as e to power minus some number u minus uc square root. So it's a typical Kosterlitz law with 0 degree. Well, then disorder, which is square root of this, remember this is delta is exponentially small as you approach, so delta c is square root in delta. So it's actually a huge region. Parametrically, it's infinitely large. How Bose glass goes between superfluid and molten. So later, so you have the one. Now the same can be done in 2D without much difference, because now just well, you have the same structure of the effective action, same imaginary contribution to the action. Well, phase integral, this is standard action. Integral over the d phi over dt is 0. If I go inside the vortex loop, it's exactly the same as taking closed quantity. Inside the vortex loop, it gets 2 pi. And I have this 2 pi everywhere in the projected area A. And if I exit the loop, it's 0 again. So whenever you have a vortex loop excitation, this vortex loop excitation picks up a phase, and the phase is given by calculating the total number of particles in this projected area in real space. Otherwise, it's a multiple of 2 pi. Q is the charge of the vortex line. Well, typically it's unit. Well, okay, you do the same estimate. You ask the question, okay, when the vortex loop has a phase of order unity. So it's 2 pi, the total number of particles in the projected area. So it's compressibility on scale r. R is the radius, times how big is the fluctuation of chemical potential in this region. Central limit theorem says it's delta. Delta is the strength of on one side times the number of sides, which is r squared. So central limit theorem says it will grow with r. So that's the expression for the phase, how it will grow with r. But just don't be confused here. It's not growing with r to the first approximation at all, because I'm talking about 2 real dimensions. So in the absence of disorder, I have u1 criticality in d equals d plus 1, and then kappa, compressibility on the given scale, it actually vanishes as 1 over r. That's the statement which comes from the properties of the model in the absence of disorder. So actually compressibility gets smaller and smaller as you approach the critical point. And this makes the cancellation of r factors in 2 dimensions. So you arrive at the following statement, that no matter what is the scale for the projected area, you contribute the same contribution to the phase. So on a more refined kind of statement, every scale contributes to the same number. When every scale contributes the same number, in RG it's actually wrong. So what I found here is the cancellation. For a given scale, you get scale-independent contribution. But then you will simply do the calculation by saying, okay, how much comes from scale 1 millimeter, 1 centimeter, 1 meter, and you see that each scale contributes equally, which means you start summing contributions from different scales and you get all. And then you have the line shape, because you say when this number is of order unity, because by the same token, correlation lengths can be converted to the Morton-Sulating gap. So it's okay. When this number is of order unity, phases of vortex loops will become important, and the RG flow towards Morton-Insulator will be destroyed, and you go to Bose glass. So that's the prediction. Now in 2D, so that's the transition line which you have in the absence of disorder. It's 3-dimensional U1 universality class with exponent roughly to third. And that's the line from superfluid to Bose glass, which is actually almost a vertical wall because it's a logarithmic dependence. So you change from 0 derivative in 1D to a vertical wall in 2D. And at this point, actually, you find that playing this game further, for example, you say, let's go to 3 dimensions. Now, vortex loops will be loops in the 4-dimensional space. What if I apply the same argument? It doesn't work because compressibility will vanish as 1 over r squared. The central limit theorem will give me 3/2. And then I find that phases of vortex excitations in 3D are always small. You don't even bother. So this mechanism doesn't work in 3D. So probably something else is responsible for 3D. We don't know yet, how to construct the theory, but numerical data looks like it's just a boring mean field shift of the critical point, nothing else. But in 1D and 2D, at least we have a handle to describe the phase diagram of the shape. So this is what happens in 3D if I plot everything close to the diagram. Looks like, the shape is not 0 derivative or absolutely vertical, looks like, probably square root. Well, this one is square root. close to square root with log corrections. Probably the same is true about superfluid body type. So both of them are kind of boring in terms of kind of functional. But the same remains true. Numerical data say that superfluid and not insulated are always separated by the body types. So according to the theorem, that's how it should be, and that's how it is in numerical data. What's more peculiar is that, well, if you calculate the global phase diagram in 3 dimensions, you actually find very bizarre numbers. So naively, I would just not expect that this is how it works. So disorder is measured in units of the hopping. U is measured in units of the hopping. And you see that superfluidity is stabilized, and it just, well, originally it was superfluid, not insulated. Now you add disorder, and you see that, well, if you have disorder and strong disorder, this is 50, this is probably, I don't remember exactly, say 70. So disorder is 70 times hopping. Remember that Anderson transition to localize a particle in a band. Anderson localization happens when disorder is roughly the bandwidth. 6 times t, and all states, single particle states in the band are localized. Now we are talking about something which is order of magnitude bigger, 70t, and it promotes superfluidity for very large values of u. So for example, here in the absence of disorder, Mott insulating gap is already measured in units of 100 hopping. So it's almost a dead Mott insulator in practical terms. But now you add strong disorder and actually have superfluid. It's a huge superfluid finger which extends here. It's also a little bit bizarre, but well, if I'm sitting here close to the Mott insulating transition and I keep increasing disorder which is necessary to produce a Bose glass is measured in units of 300 hopping. So that's how strong disorder you need to destroy superfluidity in the ground state. So here I would say we were not even been able to verify the law u to power 1/4, because the first point which we took, which is sufficiently small u, very weak interactions, this point happens to be a disorder 100 already. So probably numerically it will be very, very hard to deal with this reading. Though academically we know the law looks like a vertical wall. Interactions immediately stabilize superfluid in the ground. So that's the peculiarity, which I don't necessarily know how to explain theoretically, but that's how it is numerically. If you ask about practicality in realistic experiments, what's important is that, well, if I calculate superfluid density along this cut and along this cut, you immediately see the superfluid density in this finger. I think this is for disorder 65, so I just go along this direction. Superfluid density very quickly falls to very small value. So superfluid density in the ground state very easily gets below 10%, 5%, and even smaller. Well, the same happens if I start going in the vertical direction. I'm still in the superfluid ground state, but superfluid density is very, very small in the tail. You can measure the critical temperature, and it's extremely small. And remember that all atom experiments at the moment, they can barely make temperature comparable to hopping. That's more or less the state of the art. The temperatures are comparable to hopping, which means temperatures are relatively high, and which means in practical terms, small superfluid density translates to low transition temperature between superfluid and normal state. It's very likely that most of the fingers will be cut in a realistic experiment. So far this is kind of the cartoon, but that's what I roughly think will happen. If you do an experiment in a realistic system, always small system size, 10 million particles, at temperature roughly comparable to hopping, that's what you will see. You will see normal phase here, normal phase here. You will see direct transition between superfluid and Mott insulator. There is no way you can see the Griffiths type transition based on rare statistical fluctuations here. Everything will be mimicking a direct transition. That's what you see in numerics, and that's what you will see in the experiment. Because, well, this line is not possible to see. So it's kind of academic statement. Griffiths type transitions, you just don't see them. Because they are based on rare fluctuations, they will never fit the system. You will see kind of delayed features of Mott insulator further on, but well, here the difference between Mott insulator and superfluid is already pretty small. So if you have delayed features of Mott insulators, you are likely to see a direct transition. It will be mimicking a direct transition. So that's what my prediction, what the first experiment will probably establish. If we're lucky, we'll see that maybe this normal phase is trying to get in between them. I'm not sure about all this. So that's the likely prediction for realistic experiments. That's why I think, well, it's important to discuss all the issues, because just imagine there are no theorems, and you have only conjectures. And then you do the experiment, and you can say conjectures are wrong, and the right theory is a direct transition.
Do you think that there is any risk of lower span Hubbard model becoming somehow more unreliable? I mean, if this disorder becomes of the order of 100. I mean,
Oh, yeah. I can definitely agree with you that, well, maybe the assumptions of the single band Hubbard model will be violated if disorder is that strong. Could be. Right now, we probably have some, yeah, it's close to 100 maybe at the moment. Well, but I would say just, well, nothing in terms of the theorem, it doesn't matter whether I have single band or multi-band description. Those will be extra terms in the Hamiltonian, but they don't change the nature of state. So they don't change the nature of superfluid or multi-insulation. Simply the description of single-site physics is more complex. Yeah, probably something will change at this scale, unless people do, I don't know, additional efforts. I can stop here. I don't want to bother you with the physics of the weakly interacting Bose gas, because everything so far was about the lattice. But experimentally, well, probably the first experiments are done with weakly interacting Bose gas in the presence of speckle potential. Well, the speckle potential is essentially taking a collection of waves with random phases, and you distribute amplitudes in a certain interval. Well, if you just do this, well, in our case, we simply truncated the wave vector. We say, okay, well, if the wave vector is bigger than something, you just stop doing it. So it's only for sufficiently large wavelengths. So you just include here the wave factor, how you use the Fourier harmonics. Those are our random Gaussian numbers, and those are plane waves. So if I do the speckle potential, it has the exponential form, properties same as Poisson statistic, like average is V0, dispersion is V0 squared, so V0, the typical scale, the potential which is defined over the local correlations. Well, the correlation length, if I just truncate harmonics at lambda, the correlation length is roughly inverse lambda. The typical disorder strength will be given by whether you can localize a particle. If your potential is of scale LC and the depth of the well is V0, typical quantum mechanics said, okay, well, this is irrelevant dimensionless parameter, which is telling you that, well, in one well, you probably will start creating a bounce wave. And that's the typical shape. Well, it starts from 0, it's not bounded from above, well, but the typical value is given by the idea. I would say what's peculiar, which we don't know how to answer theoretically. Any theory done so far, it was done by Lopatin and Vinokur, and I was talking to Carlos Sadimela, he repeated it for another reason, and he said, okay, he has the same answer. So the theory was done as the lowest order account of disorder within the Bogoliubov ansatz. And then you find the disorder, the transition temperature as a function of disorder. Of course, well, this curve has 0 derivative. The actual functional curve is v to power 4, v0 to power 4, that's why it's flat top. There is no agreement here because, well, the curve, the dashed line, actually predicts transition at another point, but we shifted it vertically just to agree with the data for no interaction, for no disorder. What we see actually, well, the theory just predicts that, well, the transition temperature should start going down sharply, and they just give an estimate where this happens. The actual shape has nothing to do with the theory. It's a completely different shape. So the question is, well, essentially, okay, where the perturbation theory is true, we see nothing. It's absolutely flat top. When the perturbation theory probably breaks, but at this point they predict already significant dependence, we'll also see nothing, and then we have a dependence which is probably linear, slightly deviating from 1, because, well, you see the origin is not even 0, small chain. But the potential is already very weak, strong. So the potential is already in dimensionless, proper dimensionless units, the potential is already 6. You can easily create bound states in one well. Typical one well already has a bound state, if I neglect the rest of the system. And this is a weakly interacting gas. It's Na cubed n minus 4. And the transition temperature stays more or less the same as in the ideal system. So even very strong disorder has a very hard time to destroy transition temperature. Well, this is Na cubed n minus 6. Of course, everything goes in the right direction in the sense that, well, non-interacting gas is always localized. So the transition temperature will go to 0 if I put here 10 minus 16. But if I take realistic parameters for gases, most non-interacting, weakly interacting Bose condensates, which you create in the experiment, are 10 minus 6. So the transition temperature, very significant even for very strong speckle potential. How to explain it theoretically, we don't know. There is no theory, at least I know, regular theory explaining. Probably I'll stop here. Just one last piece of information, because people always refer, or frequently refer, to Bose glass as a state where the thermodynamics is given by T-square law for the energy, or the specific heat is linear. And this is definitely true for the following reason. Well, that's basically the argument. Suppose you have Bose glass in the limit of weakly interacting Bose gas, when it's much easier to discuss. Then I basically say, again, you have some random potential, you create localized states, and you just start filling them with particles, but you don't have enough particles to raise your chemical potential so that those lakes overlap. So lakes do not overlap, and you don't have phase coherence in the system. So the rough description of the system is in terms of localized superfluid lakes. Now, the lowest energy excitation in a lake is to add a particle. Because if I add a particle, the energy will be given by compressibility divided by the volume of the lake. So it's 1 over the lake cube. Well, if you want to do the Bogoliubov sound, it will have only first power of L. Because it's the sound dispersion relation, the energy will be inverse proportional to the size, first power. If I just play compressibility, particle excitation, where I remove a particle, the excitation energy will be only 1 over L cube. Well, but remember that the global chemical potential in a lake, this is global chemical potential somewhere. But the local chemical potential in a lake can be shifted in a finite distance. So if I'm sitting at a particular very low temperature, suppose I have this is temperature, some lakes will be close to chemical potential, so you can remove a particle from here. Some lakes will have this level close to the chemical potential, you can add a particle. Some lakes have it somewhere in between, and then you cannot do anything. And you simply count, and this looks like a Fermi statistics, because next level is far away. I'm assuming the temperature is so small, temperature is much smaller than this gap. So that's what I mean. So you have to be lucky with lower or upper level to be close to the chemical potential. And then this lake works like a site for the fermion. One boson can go, but the second one cannot go because it's already too far away. And you cannot remove a particle from here. But there's yet another lake where you can remove a particle. So you have lakes where you can insert particles or remove particles, and you simply count the probability of being lucky close to the chemical potential. You get this law. It's definitely true. But what happens next is when temperature is only sufficiently small, it's only bigger than the inverse size of the lake. And for the weakly interacting Bose gas, those lakes are big. So if temperature is bigger than the size of the lake, it basically says if you can put one particle, you can put 2 and 3, and then you essentially have a harmonic oscillator. The Hamiltonian for the lake in terms of particle numbers is a standard harmonic oscillator. How many particles you can add, that's the energy, how it behaves. So it's a simple harmonic oscillator in the variable delta n, so you have T over 2 per lake. So the thermodynamics changes from T squared for energy to linear dependence in T very quickly when temperature is bigger than the size of the lake. So that's probably the only kind of difference from the conventional picture. So very quickly in the Bose glass, this is of course the ultimate law at low temperature, but it quickly goes to linear. So I'm basically finished with that.
As there is no still 10 minutes, so we have some lot of audience.
No, I'm just done with it.
So you computed numerically this Bose glass surrounding these fingers. I mean, there are distinct regions. Have you looked at the properties of the Bose glass in those different
we
regions?
didn't study in deep detail properties of the Bose glass here or making maps of where you have
Could you
phase
call one of them the Lifshitz glass or whatever?
I prefer not to.
No?
For the following reason. Yes, in the past people were wondering whether you have to call system here Bose glass and here you have to call it Anderson glass. And so far I see no theoretical reason whatsoever to distinguish the two. The macroscopic picture is different. Bose glass here, large U, large disorder. Well, you see everything is measured on a scale of 100. So it's definitely when I say, okay, it's not a superfluid lake, it's just one site which happens to be so lucky you can put a particle there close to the chemical potential. And then maybe 1 meter away you have one site where you can remove a particle without paying energy penalty almost from the chemical potential. That's the picture. Of course, if I start traveling this way and I go this way and I go this way, the microscopic picture from one side changes to a few sides, and then it goes to lakes. So somewhere here, the picture is not one side. The picture is a localized lake. So here I have a localized lake, here I have a localized one side. But I see no fundamental difference between the two, apart from, I know, some numbers. Like here I would see a t-square law for a quite extended interval. I don't see a linear temperature dependence in the thermodynamics. Here I will very quickly see the change from t-squared to linear t. But fundamentally it's the same phase. So I would say the two phases are the same. Whether there is a phase transition between the two, I cannot guarantee. There is nothing rigorous I can say about not having a transition within the body glass. So from one insulator to another insulator, I cannot say it's a theorem. But I see no reason whatsoever to think it's a different phase. It has different microscopic properties, but on a large scale, it's the same stuff, as far as I see. Microscopic characterization can be completely different. That's why I mentioned thermodynamics, but here it can be quite different. Yeah, though you can find in literature sometimes people draw a dashed line and say, okay, maybe those two glasses are different.
And a third glass intervening between the moths and so forth.
Maybe. No. At this point I would say just, well, if it's not forbidden by theorems, we can only check. So I cannot say immediately no. I don't know why. If it is for the Bode-Hubbard model, maybe there is nothing. But maybe you can cook up a model which is different.
No questions? Kids and thanks for speaking.
Good.